If I try to balance a block on the edge of a table in such a manner that I keep on stacking these similar blocks one on top of the other over and over again, trying to maximize the distance of the topmost block from the edge of the table. In such a scenario, the question is, how many of these blocks can I stack on top of each other? And how much further can I go beyond the edge of the table in such a manner that the overall system does not fall? To study this problem, first of all, we're going to look at a one block system where we try to balance a one block on the edge of a table. Then a two block system where we try to balance two blocks on the edge of a table, and three blocks, and on to come up with an expression where we can theoretically balance n number of blocks on the edge of a table to achieve maximum overhang. That is, how much further can we go from the edge of the table to the edge of the topmost block, let's suppose, to create a stable configuration. For that, we have, let's suppose, a block which has a length of, let's suppose, capital L and a mass of small m. And we're going to consider blocks that have uniform mass density, so that the center of mass of this block lies exactly at the geometrical center. That means the center of mass of each of these blocks that I'm going to consider must be at the geometrical center along its longitude. That means it must be L/2 distance from either of these edges. So if I have these kind of blocks which I'm trying to balance, then what is the general principle based on which I can balance this system? The general principle of how you balance an object on the edge of a table, let's suppose, is very simple. You try to make sure that the center of mass lies on the edge or inside the edge of the table. So let's suppose you're trying to balance this block. Then you want to make sure that the center of mass of this block 1 either lies on the edge or inside the edge. This is where the center of mass is supposed to lie. The reason is because the moment I place it on the edge, then I can divide this entire region into two portions, the left hand side of the center of mass and the right hand side of the center of mass, such that both have equal contributions towards weight. So this will have a contribution of m/2g, and this region will have a contribution of m/2g, right? So in such a manner, since both the forces acting on both the sides or both the portions of the block are equal, then the block is theoretically balanced on the edge of the table. So this is the general principle. If you want to balance an object on the edge of some table, you want to make sure that its center of mass lies within or at the edge of the table. Now for a one block system, it is kind of obvious that the center of mass lies at a distance of L/2 from the edge of the block. So that means for one block system, the maximum overhang is L/2. So for a one block system, we can create a stable configuration and maximum distance of L/2. Now let's go on to the second system, which is a two block system. Now when we have a two block system, first of all, I want to balance block 1 over block 2. That's obvious. But I also want to balance the combination of block 1 and 2 over the table. Yeah, so I want to balance block 1 over block 2. But I also want to balance the combination of 1 and 2 over the table. So to balance block 1 over block 2, the conclusion is very simple. If I want to balance block 1 over block 2, then I need to make sure that block 1 is hanging in such a manner that its center of mass lies exactly on the edge of block number 2. So this is the center of mass of block 1. That means it is at a distance of L/2. But that itself is not enough. It's not just enough to balance block 1 over 2. I am also interested in balancing the combination of block 1 and 2 over the table, which means that I also have to balance the center of mass of 1 and 2 on this particular edge. If I want to balance the center of mass of both block 1 and 2, so I want to make sure that the center of mass of 1 plus 2 must lie on the edge. Then the question is, what should be the length of the distance of block 2 from the edge? Okay, so let's suppose in that kind of a situation, the distance of block 2 from the edge is given by x. Okay, so I'm going to consider this particular problem where the edge is at 0, or let's suppose this is the center of this x-axis. Okay, if I'm considering this as the x-axis, then this is the center of the x-axis, the edge. In that kind of a situation, first of all, block 1 will be balanced on 2 if its center of mass lies exactly here, right? And the block 1 and 2 will be balanced on the edge if the center of mass of this configuration lies on the edge. So let's suppose the center of mass of this entire configuration is given by the 0 coordinate in the x-axis. In that kind of a situation, you know how to calculate the center of mass. In the denominator, you have mass of block 1 and the mass of block 2. Now, what is this position of the mass of block 1? The position of the mass of block 1 is given by the position of the center of mass of the block 1. The center of mass of the block 1 is at a distance of x-axis from 0, right? Now, what about the center of mass of block 2? The center of mass of block 2 is somewhere here, right? It is at a distance of L by 2 from its edge. The center of mass of block 2 is at a distance of L by 2 from its edge. Now, since the edge of the block 2 is at x from our coordinate reference, and the center of mass of block 2 is at a distance of L by 2 in the opposite directions, so according to our coordinate with respect to 0 of the edge, the center of mass of block 2 is at x minus L by 2. So this entirety gives us the center of mass of both the systems 1 and 2 combined. So now if I want to calculate what this x is, this simply gives us mx plus mx minus ml upon 2 is equal to 0, or I end up getting 2mx is equal to ml upon 2, or m and m gets cancelled out, so I end up getting x is equal to L upon 4. This simply means that this distance is equal to L upon 4. So if I have a 2-block system, the topmost block must be at a distance of L by 2 from the block number 2, and the edge of the block number 2 must be at a distance of L by 4 from the edge of the table. So this gives me a maximum overhang of L by 2 plus L by 4. While in the first case, the maximum overhang was given simply by L by 2. Now, if I want to complicate this system further and add an additional block to create a 3-block system, all right, now what will happen then? Again, same principle. If I want to balance block number 1 over block number 2, then obviously the center of block 1 must lie on the edge of block 2, which tells us that this should have a length of L by 2. And if I want to balance both 1 and 2 over block number 3, then according to our previous calculations, this region or this distance should be equal to L upon 4. Now, if I want to balance block 1, 2, and 3 on the edge of the table, then I need to make sure that all these 3 has a center of mass which is on the edge of this table. This is where the center of mass of 1 plus 2 plus 3 should be, while this is where the center of mass of 1 and 2 is, and this is where the center of 1 is. Again, I perform the same calculations. I consider the edge to be the reference of 0, and I consider this to be a distance of x. So then the center of mass of 1 plus 2 plus 3 is simply equal to 0 in the x-axis, right? So on the bottom denominator, I'll simply consider mass of 1 plus mass of 2 plus mass of 3, right? And on the numerator, I'm going to consider the mass or the center of mass of 1 and 2. Where is the center of mass of 1 and 2 combined, right? Based on our calculations previously, the center of mass of 1 and 2 combined is here. This is where the center of mass of 1 and 2 combined is. So that is center of mass of 1 and 2 combined is at a distance of x from x is equal to 0. Where is the center of mass 3 at? The center of mass 3 is at x minus L upon 2. So it is at a distance of x minus L upon 2 somewhere here. All right. So in that kind of a situation, so what is x? So in that kind of a situation, x is 2mx plus mx minus ml by 2 comes out to be ml upon 2, or 3mx is equal to m capital L upon 2, or x is equal to, so m and m gets cancelled here, it simply comes out to be L upon 6. So here x is supposed to be L upon 6. That means the maximum overhang possible is L by 2 for the topmost block, L upon 4 for the second topmost block, and L by 6 for the third topmost block. This is the maximum overhang possible. Similarly, let's go further in the 4-block system. In the 4-block system, the center of mass of block 1 to be balanced on top of block 2 must be here at a distance of L upon 2. So this is the center of mass of block 1. And similarly, the center of mass of block 1 and 2 combined must be somewhere here, 1 and 2 combined, such that this particular distance is L upon 4. And again, similarly, the center of mass of block 1, 2, and 3 combined should be on the edge of block 4. So this should be 1 plus 2 plus 3 combined somewhere here. And according to our calculations, this distance is equal to L upon 6. So the remaining distance that I'm interested in finding is this particular distance. So where should be the center of mass of 1, 2, 3, and 4 combined? It should be on the edge of this table. It should be on the edge of this table. So 1 plus 2 plus 3 plus 4 combined should have a center of mass at, let's suppose, x is equal to 0, where this is x. So in that kind of a situation, if center of mass of the entire system combined is at this reference of 0, then in the denominator, you will of course get 1 plus 2 plus 3 plus 4. And then you will have the center of mass of 1, 2, and 3 combined at distance x, right, at here. So mass 1, 2, and 3 combined has a center of mass at x, and the remaining block 4 has a center of mass at m, x minus L by 2. So let's suppose the L by 2 is here, the center of mass of block M4 is here. So this is nothing but x minus L by 2. So this simply gives us that 3mx plus mx is equal to ml upon 2, which gives us a condition that 4mx is equal to ml upon 2, where m gets cancelled, and we are left with x is equal to L upon 8. So x is equal to L upon 8. That means the maximum overhang possible here is L upon 2 plus L upon 4 plus L upon 6 plus L upon 8. So as you can see, if I'm trying to balance blocks over each other, not only do I need to, let's suppose, balance 1 over 2, I need to balance 1 and 2 over 3, and I need to balance 1, 2, and 3 over 4, and then I need to balance 1, 2, 3, and 4 over the edge, and on like that. So initially, when we just had one block, the maximum overhang was L by 2. When we had 2-block system, the maximum overhang was L by 2 plus L by 4. In 3-block system, the maximum overhang was L by 2, L by 4, and L by 6. And in 4-block system, you have a maximum overhang of L by 2, L by 4, L by 6, L by 8. Do you see a pattern here? If you keep on continuing these calculations for 5, 6, 7, 8, 9, 10 blocks and on and on and on, what you will find out is that you can create a configuration of maximum overhang from the edge of the table such that the topmost block has a maximum overhang of L upon 2 from the second block. The second block is beyond the edge of the third block at a distance of L by 4. The third block is beyond the edge of fourth block at a distance of L by 6. The fourth block is beyond the edge of the fifth block, let's suppose, at a distance of L upon 8. Let's suppose this is the fifth block. And the fifth block is at a distance of, let's suppose, L upon 10. Do you see the pattern here? For an n block system, the maximum overhang is L upon 2 for the topmost block, L upon 4 for the second block, L upon 6 for the third, L upon 8 for the fourth, L upon 10 for the fifth, and on and on. So this can be simplified to, let's suppose if I take L by 2 as a common, this can be quite simplified to, let's suppose this is 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4 plus 1 upon 5 and on and on. This is an infinite series. So if I take the L upon 2 outside, I'll end up getting a summation where let's suppose n goes from 1 to some capital N where I have a small n here. So this is an infinite series of 1 upon n and going from 1 to some higher number. What is the value of this sum? The value of this sum is going to give us what is the maximum overhang possible for an n block system. Now, if you're interested in finding out what is the maximum overhang possible for an n block system, let us just add up these terms using some program, let's suppose. So here I have created a very simple program of adding up the reciprocal of numbers, the series that we obtained, for the first 10 terms, the first 100 terms, for the first 1,000 terms, 10,000 terms, 100,000 terms. So let's see what kind of sum we get. So if I run this program, this is what I get. The sum of the first 10 series is something like 2.92896, something like that. Sum of the first 100 terms is 5.187, 1,000 terms 7.485, 10,000 terms 9.787, 100,000 terms 12.09, on and on. What is interesting is that this series does not converge to a finite value. This infinite series is actually a diverging series. In fact, this particular series sum is known as what is called a harmonic series. A harmonic series is a sum of these terms: 1 half, 1 by 3, 1 by 4, 1 by 5, on and on. And this harmonic series, as it turns out, does not converge to some fixed value. In fact, it diverges, which means what? It simply means that if you look at this this term L by 2 and summation from n is equal to 1 to capital N, 1 upon n, then if this n tends to infinity, then this series sum will also tend to infinity. We have found out the answer to our original question. What was our original question? Our original question was how many of these blocks we can stack on top of each other so that we can achieve maximum overhang, that is maximum distance from the edge of the table, without disbalancing the configuration. So theoretically speaking, we can stack up infinite blocks, one on top of the other, and the maximum distance from the edge of the table tends towards infinity. Since the series is a diverging series, it's an infinite series, the maximum distance possible theoretically beyond the edge of the table actually tends to infinity, and the number of terms or the number of blocks also tends towards infinity. So this is the interesting block stacking problem. It is based on the very simple principle that you want to balance a system in such a manner by placing the center of mass on the edge or inside the edge. If you place the center of mass of the topmost block inside or on the edge, then the allowed length is L by 2. And for the second block, the allowed length is L by 4. And for the third block, the allowed length is L by 6, because in that case, not only you will have to balance the first block on block number 2, you'll have to balance 1 and 2 over block number 3, and you'll have to balance 1, 2 and 3 over the edge. And if you repeat this calculations over and over again, you see this emerging harmonic series pattern. It simply says that you can have infinite blocks and a maximum overhang tending towards infinity. So that's all for today. I hope you found this interesting.